you can cancel out omega t plus phi
Almost.
And the cosine.
cosine.
These are linked together. You
Yeah.
can't get rid of just this piece of it.
Yeah,
You have to get rid of the whole
cosine.
thing. So the whole thing goes away. All right, what else can we get rid of?
Let's see.
Get rid of 1A.
Yep.
1A.
We get rid of one more thing.
The negatives.
Negative.
And so what we're left with on the left-hand side is m omega squared, and on the right-hand side, k. Solving for omega, I first get omega squared is equal to k, which is the spring constant, divided by the mass. And so omega is the square root of k over m. And so if something is obeying Hooke's law, that is going to be the formula for the angular frequency. Now, for things that are obeying Hooke's law, we have a special name for it, of course, and that is simple harmonic motion. So if you see reference to SHM, that's what I'm talking about, simple harmonic motion. Now the harmonic motion means that it's moving back and forth, it's oscillating, we have this repetitive motion going on. It obeys Hooke's law, that is part of it. And the simple piece is the fact that it goes on forever. Or until something physically stops it. If it started vibrating back and forth, so here's an example of harmonic motion that is not simple. The fact that it eventually stopped, that is damped harmonic motion. And we are not dealing with that, we're dealing with the simple case, the fact that it will not stop. But damped harmonic motion, if we plotted it, it basically is what the same cosine curve, except the fact that the amplitude is changing as we go. So reality for a lot, but you know, as with anything with physics, you start out with a simple case and then you start adding reality as you go. All right, questions to hear?
What would an example of a simple harmonic motion be?
Well, something that models it closely would be that.
Wouldn't it stop eventually?
It will, I said, models it closely. I mean,
The only thing that I can think of that does that is the single electron shell and a cesium atom, which is it oscillates like this 9 billion times in 1 second, and that's what we get for a second, exactly.
Or,
That works.
And
or,
it's always happened, it always is that.
they modeled in when you get to quantum, what's known as a harmonic oscillator.
or your frequencies in radios, because you have certain frequency and you have certain harmonics in that frequency, and like you cut it on and you hit somebody else is on your frequency, and because you have a bandwidth and the harmonics you might pick up, and it causes distortion.
So in a case like that, when you're talking about radio frequencies, that what keeps it from being damped harmonics is the fact that you have an additional power supply that's constantly boosting that amplitude back up to some level. That under normal circumstances, it would eventually peter out, but I'm mixing two things here, I'm realizing as I'm speaking. But part of what a power supply does is to maintain it at a cost of something else. I mean, you're not gonna do anything without a cost of something else. And then you get into the second law of thermodynamics, where you're always gonna lose energy. And ultimately, the heat death of the universe. Okay. Now we need to connect it to a couple other vocab words. So you notice that when, so cosine of t, how much time takes place before it starts to repeat itself?
2 pi.
2 pi.
All right. If I had cosine of 2t, how long before it repeats itself?
1 pi.
If I had cosine of 3t, how long before it repeats itself?
A third of 2 pi.
So we can generalize this by saying that the amount of time it takes for it to start to repeat itself is just 2 pi divided by omega. The amount of time it takes for an object, for repetitive motion to repeat itself, or to produce one wave, is known as the period. And so now, for something in simple harmonic motion, we have another formula. So the period is equal to 2 pi divided by the square root of k over m, which is 2 pi times the square root of m over k. Let's see how well this works. So what I'm gonna do is I'm gonna set this up. I need, I got that one there, so we need a right angle. Let's see. Probably be helpful to have 2 of these. This needs to be close enough. And I need to do it off the edge. Very similar to what you did in the lab yesterday. First thing we need to do is figure out what the spring constant is. So I need a set of masses that I'm going to attach to it. We'll see how far it stretches as we add masses. Just going for a crude approximation here. So it is about 76 centimeters is from the ground. So when the added mass is 0, we're at position of 76. Let's do it in meters, 0.76 meters. I'm gonna add 10 gram mass to the bottom rung. Now, I was doing this experiment. If that thing falls off, then I would have to start over because I would need to know the exact number of coils up here. If I added more coils, I'd have a different spring constant, like that. Yep. So what I'm gonna do to offset at least some of that, I'm gonna grab a rubber band or two. And so attach the rubber band to this part right here so that it'd be easier to set back up. And hopefully the rubber band doesn't get sort of trapped in the spirals to the point where I have to cut it. Also provides a little bit more friction. So let's get that to calm down. So that is so 73.5 centimeters from the ground. And then I take my 10 gram mass, which I did something with. Did it fall off or did I take it off?
I thought you had it on a spring, it might have popped off.
Yeah. All right, we'll start with the 20. Coordination issues there. All right. Now, in reality, as I put it on the end there, it's not flat anymore. It's like this, and so I'm basically going to take the middle of it once it calms down. And so the middle of it about 59 centimeters. 0.02 and 0.59. So that was 20, so now we'll have 40 on it. And hopefully it'll stretch twice as far as what it just stretched. About 46 centimeters. That, we'll go with this. Now technically, my position is what I was controlling, and, I'm sorry, the mass is what I was controlling, and the position is what I was then measuring. So 0.02, 0.04 in kilograms, and then, let's actually look at displacement. So mass, and then displacement, magnitude of displacement. So 0.02, 0.04. So initial position is 0, it's at 0, so my displacement was 0 to start with. I tacked on a mass there and it stretched out 0.145. Is that the difference? And then 0.13. Oh, sorry. I want that. 0.275. Oh, okay about that. So 0, 0, then 0.1, 0.2, 0.3. like that, and then 0.04, about right there. You got the line of best fit. So the slope of that, well, if I think about the forces acting on those masses, I have the spring force acting up, so I have a force, I'll put some E for an elastic force, and then I have weight acting down. So I got weight down, I got this elastic force acting up. It's close enough to equilibrium that those should be equal to each other. And so this is equal to K times its displacement, and that's equal to the weight. So I plotted basically my displacement versus my mass. And so I'm trying to get this into slope-intercept form. I know that it was mentioned earlier, y equals mx plus b. Now I don't use m for slope because we use m for too many other things. So I use a dollar sign. And so my y value is my displacement, so I'm solving for delta x. And I divide by k, so I end up with k over g times my mass, which is my horizontal, plus 0. So in theory, this is what the graph is. In other words, my slope is k divided by g. My y value is delta x, my x value is m, and my slope is k over g. So k would have to be my slope times g. So it's a matter of finding out my slope. I think in the lab that you just did, you're doing not m, but the weight. You're doing the force down here, I think.
Yeah.
Okay. What was that? You just displacement versus
Displacement is force.
Okay.
So you divide and,
The difference is the acceleration due to gravity here. So my slope is whatever that slope is, and I'm just gonna take it's a crude approximation for what I'm doing. Technically, you would plug it into Excel or your calculator, and there's an official formula for how you find slope from a set of data points for the line of best fit. But for what I'm doing right here, just gonna do rise over run. It's close enough to linear for what I'm doing, so I'm just gonna take this divided by that. So 0.275 divided by 0.04. If someone would be kind enough. $6.875?
Yes.
All right. So K over G, my slope, is 6.875. And so K is 6.875 times G. $9.8. Something's off. I added 40 grams, then I stretched it.
$67.375.
That number's gonna be too big. Something's off. All right, that was 40 grams I added. Yeah. 40 grams is 0.02, or is 0.04 kilograms. O. V delta x equals mg, good with that. We have delta x right there, so delta x equals. Ugh. G over K. So K is equal to 9.8 divided by 6.875. Because we were about to get an answer that was somewhere close to 70 newtons, and I thought, there's no way I need 70 newtons to stretch this thing 1 meter. Considering it only took about 0.4 newtons in order to stretch it
I got
a third of a meter.
1.425 newtons.
All right. So my value of K, my spring constant, that is newtons per meter. It says that I need 1.425 newtons in order to stretch this thing 1 meter. So now we can make a prediction here. The period is 2 pi times the square root of m over k. We have a k value now. So we get 2 pi times the square root of, we'll just stick with the 40 grams there, so 0.04 kilograms over my spring constant, which is, just told me, 1.425. So what is our prediction for the period?
Square root